welcome to our Rutronik webinar series, Rutronik Connect. In our first webinar series, we will concentrate about Wi-Fi technologies. You'll learn all about the latest Wi-Fi 6 and Wi-Fi 6E and Wi-Fi 7 standards. Today, I would like to welcome Nick Wood from our supplier Inside SIP with the topic about Wi-Fi 6 and why Wi-Fi 6 is the Wi-Fi for IoT upgrade. The duration will be 1 hour and questions can be typed on the right sidebar. We will answer them at the end of our presentation. And in addition, the presentation will be recorded and afterwards you will receive the slides from us. Now I also will hand over to Nick. Hello, Nick.
Hi. Okay. This presentation is going to be about Wi-Fi 6 and why I believe the right way to think of this is the upgrade for IoT. So in terms of the agenda that I'll be presenting today, I'll give a very brief history of Wi-Fi, an explanation of the key changes in the Wi-Fi 6 upgrade, and why it's a little bit different to ones that have come before, and leading on from that stuff, which is essentially the technical details of what's changed, I will then move on to what this means in practical terms, in terms of IoT and IoT applications. And then in particular, what that means for end device components. I mean, I'm not really talking about routers here. Routers obviously is a whole other domain, but it's not so relevant for the electronic component side of it. And finally, I will talk briefly about what Insight SIP has to offer. This isn't a product advertisement. It's a what I hope will be an informative webinar, but I will briefly present our solutions. So moving straight on, because there's quite a lot of technical stuff to go through here. Brief history of Wi-Fi. So here you've got the different generations of Wi-Fi. Wi-Fi 0 was never it was never actually called Wi-Fi 0, but I've it's been added here effectively for convenience. But what you see is that each generation was basically about giving you an order of magnitude more speed, fundamentally. That's what the prime aim was. So you see it going from the early days of a few megabits to seconds to the gigabit level we have today. But what you might notice is that with Wi-Fi 6, there's a little bit of speed upgrade, but that's not really the main point. And actually, the lower end goes down, funnily enough. So what's this about? Why did they bother with an upgrade to give you a fairly small percentage speed increase? Well, the answer is it's not really about upping the speed particularly. So this isn't meant to be a physics lesson, but I'll just briefly dive into one of the fundamental problems of wireless technology. Is you've only got a limited amount of spectrum to play with. It's with a wired internet, you can just get another fiber optic cable and lay it down and double your capacity. Okay, it's a bit more complicated than that, but fundamentally you can keep laying cables and better cables, but you don't have that option with wireless. We can't design a better air, and we can't put two things in parallel. So what can we do? Well, all you can do is divide up more cleverly what you have. So with radio frequencies, you can divide it up spatially, meaning you direct signals in a particular place and direct other signals in a different place. You can split up in time, so you send signals to one place at one point in time, and then the next point in time you send them somewhere else, and you can split up by frequency. But even in frequency, you've only got so much to play with. The lower frequencies just aren't very useful for you, and the higher frequencies, unfortunately, can kill you. So you have a narrow band of frequencies that you can, practically speaking, work with in like what you call this RF and microwave place. So you've got a limited stuff to play with, and so you have to be quite clever in how you use it. So you can add bands. So in Wi-Fi 4 and 5, they added 5. Originally, it's 2.4 gigahertz. You added 5 gigahertz, and then in Wi-Fi 6, you also have a 6 gigahertz band in some places, not all over the world, in fact. But to make use of the spectrum, you have to have better devices, better sensitivity, better frequency accuracy, better power amplifier linearity. I'll explain these a bit more later on. So this is what you're up against with wireless devices. So what can you say about Wi-Fi? Well, you can get obviously a lot of high performance out of it. It can be the backbone of home and office networks, and in many situations it works well. Where does it fall down? Well, networks can get quite easily saturated. You have a limited number of channels. You have other uses of the spectrum, especially in 2.4 gigahertz. There's a lot going on there. You've got Bluetooth there. You've got Zigbee. You've got proprietary things. You can have Thread running there. So you have a lot of competition for especially that band. Its performance degrades quite rapidly with distance and with obstacles, and it does consume a fair bit of power. So if you get a lot of things in the same place, it starts to fall over and not work so well. So what's changed with Wi-Fi 6? Well, there's a number of different elements tackling different parts of that problem effectively. So the first one goes by the rather mouthful of orthogonal frequency division multiplexing. This is basically about splitting up the data bandwidth more finely. So if you think of the bandwidth as the size of your data pipe, how much data you can pump through it at one time, Wi-Fi 6 effectively, it's not making that bigger. It's not allowing you to pass more data in total, but it's allowing you to use multiple smaller pipes instead of one big one. So where is that useful? Well, it's basically if you've got lots of devices, but they don't necessarily have a huge amount of data each to transmit. So the idea is this can give you better overall throughput by carving up the bandwidth to what each user needs. What this ends up with, what the aim is you get better overall throughput. You get better latency, so you're not waiting for your turn. You can send multiple things at once, and you can therefore support more devices. What's the downside? Well, you need better devices because you need to, certainly your router gets a lot more complex because it's got to do a lot of clever management of slots and setting who to transmit when, what, and you need to control the frequency very tightly. You've got to focus in on these narrower bands. So if I try to just represent kind of what this means visually, so if in Wi-Fi 5 you might have these end devices, so each has got some data to send, but it doesn't necessarily have a full frame worth of data. But unfortunately, in the old Wi-Fi 5, you have to send a whole block, whether you fill it up or not. So in this, you have each one will send data one at a time, and it takes 3 blocks worth of time to get this data sent. With Wi-Fi 6, you can effectively send them all at once because you have narrower pipes. You're not sending more. You don't have a higher throughput, but you have more pipes to send it through. So in this one, they all go through at once to the access point. So this is a way of supporting more devices more intelligently than in the Wi-Fi 5. The next major upgrade is target wait time, which is about improving the power consumption side of the equation. So previous devices need to regularly communicate with the access point, or else the connection was broken. So if you're like in a streaming situation where you're like streaming video or something, well, that doesn't really make any difference. But if you've got devices that want to send data sometimes but not always, they were still having to wake up and send data just to communicate with the access point quite regularly. Under the target wait time, end devices with nothing to do can negotiate a longer wait time. So you can basically, the device can tell the access point, right, I'm not going to have anything to do for a couple of minutes or whatever it is, whatever the interval is, and then just go to sleep. End devices with can also just choose sort of to sleep as long as they want and then wake up and contact the access point. So in this sense, this allows Wi-Fi devices to behave a bit more like Bluetooth Low Energy, in that end devices with low or infrequent data requirements can sleep for extended periods. And obviously this is a massive help in power saving, because basically if any RF device, more or less, when does it consume power? Well, the most power it consumes is with the radio on, nearly always. The radio consumes the biggest amount of power. The next step down is when if it's got a microprocessor running. Even if the radio isn't on, that will consume quite a lot of power. And then if you can just go into a sleep mode, then it can be quite low power. So this gives you the possibility, at least, of extended battery-powered operation. Another improvement is what's called network coloring. One problem you can have with Wi-Fi, especially if you've got multiple access points, so you might have 2 access points. Let's imagine a simple situation. You have 2 access points covering different parts of the same building. So one is covering, say, one office, and the other's covering another office. Now, there's always going to be, if you're going to cover if these offices are adjacent, let's imagine, then there will be some overlap between these networks. Now, previously, what happened is if a particular channel was being used, is detected as being busy, the device has to wait. The device has to wait and then wait for the channel to be clear. And obviously this can, if you've got quite a lot of overlapping networks, this can cause quite a lot of blockages. What this network coloring, as it's so called, I mean, they're not really colored, it's just a phrase, it allows you to distinguish between the 2 networks. So in the example here, your user 2 might see some signal from access point 2, but if that signal isn't a particularly strong signal, it can ignore the fact that it's using the channel on the basis that it will probably be sending the data away to its own access point, So it doesn't necessarily have to wait for a channel to be completely clear if it basically can guess that the signal probably won't interfere with its own communication with the access point. So basically, this allows you to sort of not be so concerned about interference from a different network. It doesn't mean that if you've got a very high signal in a particular channel, you still can't use it. But if you've got a smaller signal, you can operate with a different threshold, and then that does allow the two networks to work better within that overlap zone. So that's another way of improving the sort of throughput of multiple devices. So then the final one this is the part that does give you a little bit more speed. This is about basically how you code data in your RF. So what they call quadrature amplitude modulation. So it's quite a technical point, but basically a symbol in Wi-Fi consists of an amplitude and a phase, and the more finely you can divide up sort of gradations of phase and amplitude, then the more data you can transmit at a single point in time. So what Wi-Fi 6 does allow is you to go up to what they call 1024 QAM, which basically means you have more granularity of phase and amplitude at a single point in time that you can refine into a symbol, and that allows you more bits per symbol, effectively more bits in a particular moment in time. Now, yeah, but let's be clear that you can only benefit from this if you've got a very good low noise environment. You typically, this only works fairly close to the access point, and you need to have better sensitivity in your receiver, and you need high linearity in your power amplifier, because you're trying to distinguish between quite fine gradations of levels of output. So you're only really going to get the best of this in ideal scenarios, but there is a little bit of extra speed there if the conditions are right. And then the other point that I'm going to raise is multiple in, multiple out streams, which is about separating the data spatially. So basically, your access point can do what's called beamforming, which means it sends data out in a particular direction. It uses its multiple antennas to send data out in one direction, and it can send different data out in a different direction. So the idea is then you can divide up spatially. And in Wi-Fi 6, this allows you to do uplink and downlink using this multi-user MIMO technology, which is another way of getting the most out of your spectrum. So those are the key technical upgrades available, and as I hope it's been clear, they're not mainly about increasing the speed, that they're about increasing the efficiency and flexibility of utilization. So that's all a lot of interesting technical whatnot, but the question is, what does it really mean in practical terms, and what's this got to do with IoT? Well, what is Wi-Fi 6 good for? So if you just want to have some super fast connection between an access point and a single device, it's not really going to change your life, to be honest. So you want to do some super whatever high grade video gaming scenario, it's not going to change much because that's not really what it's for. What it can work offer you is when you've got dense networks, so you've got lots and lots of devices around, you've got some of them battery powered, maybe the data demands per device aren't huge, but you've got lots and lots of them, and that is the scenario where Wi-Fi 6 comes into its own, because you won't get so much contention, you won't get delays, you won't have latency, and the higher bandwidth devices can get the spectrum they need, and whilst the low bandwidth one can slot in the gaps effectively. So, how in terms of IoT, well, that's exactly the scenario that, I mean, IoT is obviously a bit of an umbrella term and can cover lots and lots of types of applications. But yeah, typically what you're talking about is not huge data rates, but lots of devices, large networks, maybe some devices at least battery powered, so they can just be installed easily without any great fuss with wiring, and that's where this Wi-Fi 6 version really comes in. So talk a little bit about, well, isn't that what Bluetooth Low Energy is for? Yes, obviously it is, and effectively Wi-Fi 6 has to some extent stolen some ideas from Bluetooth Low Energy. What are the so there is a little bit of convergence there, I would say. There's a little bit of convergence there, but they're still quite different technologies. BLE obviously is very resilient. It's, with its frequency hopping technology, I'm not going to talk about BLE here, but it's more resilient than even Wi-Fi 6. It can be very low power, and it offers a simple local point-to-point connectivity, especially with a device like a phone. So it still wins on those points. It's relatively low bandwidth, so you don't get a lot of data through it, though. It's still limited to 2 megabits a second, whereas Wi-Fi 6, that can give you much higher data rates. It's not going to hit the same power consumption levels as BLE. What you do have is a direct connection to an IP-based infrastructure. You connect to an access point, and then you've got an IP connection pretty easily onward from there to wherever you want to go. You can connect to the cloud easily. Bluetooth Low Energy, you have to have some sort of gateway function sitting in there. It doesn't naturally connect directly to the cloud. So the two are moving together a little bit, but they're still got their distinct pros and cons. So what does this mean for devices? Well, previous generation of end, I'm talking about end devices here. I'm not talking about access points, which is a whole different, routers. They're obviously much more complex beasts. But typically, previous devices used an external host CPU. They didn't really worry too much about power consumption. Quite often they would be like AT command driven type things, and they basically were like Wi-Fi as an add-on quite often to quite big complicated microprocessors running maybe a Linux type application. Not necessarily, but that was generally the kind of architecture that you had with previous Wi-Fi devices. What at least some of the new generation are, and there still are Wi-Fi 6 devices of that type. I mean, they do exist, but a kind of new generation of device now is one that's more, again, perhaps a bit more of the architecturally speaking, like a Bluetooth Low Energy device, which has a powerful internal CPU. It can form the core of an IoT device. So you just add sensors and some interface, human machine interface to control it, but it can be the hub of a quite sophisticated device. So such a device that has user accessible memory, has an open processor. These days you've got to think more and more about security, so you would perhaps have a security subsystem to manage keys and make sure that it can only be securely updated. You would want clever power management in there to go to sleep and do those things. And you may not be looking to maximize the throughput, but more make a deliberate choice to limit that, because if higher bandwidth radios tend to consume more power. So you can make a choice to have a lower bandwidth radio so that you can really operate a low power device. So what you're looking at is a kind of quite different device to previous sort of versions of Wi-Fi. So I'll now move on to what Insight SIP has to offer here. So briefly, for anybody who's not familiar with Insight SIP, we are a wireless module supplier. So we do fully integrated wireless modules. That's what we do, and it's all we do in miniature packages, and we integrate antennas in them. So you need all of our products. It's literally just a question of putting the module on the board, connecting some power, and you have a fully working radio node and transmitting over the air. And that's very much our products. They're all really of that type. But in the Wi-Fi 6 in particular, obviously, which is the subject of today's webinar, we have a dual band Wi-Fi 6 BLE module, and it's very much designed for this IoT type application that I've talked about. It's in a miniature 12 by 12 millimeter form factor. It's a dual band covering 2.4 and 5 gigahertz. It's got integrated antennas for both those bands. As I said, it's this model of what we call a fully complete RF node. Not all modules are, so it's got everything inside, all the crystals, the matching, decoupling. So basically, you put this on a board, you connect some power, and you have radio connections with Bluetooth and Wi-Fi. This part on its own could, for example, form a Bluetooth to Wi-Fi bridge with suitable software on board, for example. It's got onboard 4 gigabytes of flash memory, so there's plenty of application space. That can be extended with external memory should you wish to do so. It can, as well as Wi-Fi and Bluetooth, it can also support Thread and Matter. So for smart home applications, if you wanted, you could build quite a sophisticated battery-powered application using Matter, using essentially this product as the core, and just connect whatever else you want for that particular application. And this is based on a NXP chipset, which is the RW612. It also has a complex security processor on board as well, our full ARM Trust Zone and NXP's own add-ons to that. So you have a very secure method of controlling, say, updates, for example, where you can have fully signed and encrypted updates sent to the device that you can be sure are the right thing. So what's this aimed at? Well, it's aimed at just the kind of applications I was talking about earlier. It's aimed at being an end node in some kind of dense network, and possibly one that could be powered by battery. It's not designed for super high speeds. That's not what this is about. So it actually only supports the lowest channel in terms of the possible channel widths you can have, which, I mean, channel width is essentially like how big is the data pipe. So it supports the small one. It still gives you some quite good, impressive data rate, but it's not about super high speed. It's about being able to operate in this IoT scenario. So, you know, what could it be used for? Well, advanced wearables, smart home devices, some large industrial installations, or some building management applications. I mean, there are many diverse things in what one generally calls the IoT domain that you can imagine this is going to be used for. But it's where, you know, essentially BLE is not giving you enough connectivity, or the processor on board, typical BLE devices isn't giving you enough, but you still want to, you know, relatively, you're not talking about a big system. So this is the kind of application this is designed for. So what kind of battery operation are we talking about? Well, there is still a difference between BLE and Wi-Fi. So BLE, you know, you could run potentially off something as small as a coin cell if you really are doing the sort of low sleep mode type situation, and ones that are perhaps connecting more often. You could talk about, you know, AAA batteries, maybe up to AA perhaps. By contrast, these kind of devices are going to be bigger batteries. So if you've got a very sleepy, as it were, application, one that's only waking up occasionally, you could maybe run off a couple of AA batteries. Perhaps one of the bigger batteries is more realistic in practical terms. So there is still a difference between BLE and Wi-Fi, at least as of today. And, you know, long sleep time applications, you know, it's got to be a very long sleep time, because once the radio's on, then you do consume more power. But at least gives you an idea here of what might be possible. So, yeah, where does this fit into the ecosystem? It's basically designed as the hub of an end node. So you know, you want somewhere you want to use the onboard processor, somewhere you want to use the large memory, something that can be capable of low power, perhaps not necessarily, and secure. Security is also a big thing that shouldn't be underestimated. And where connectivity to the cloud is also another key feature, that you then connect to a router, and onward from there. So you can still, I think I've kind of repeated this a few times, so I think hopefully the point has sunk in by now. Also, just want to briefly talk about Matter. So this is an open standard promoted by a lot of industry players, so Nordic, NXP, Google, Apple, and various others. So this is an application level protocol that runs on different underlying transport. So you can run it over Bluetooth, you can run it over Wi-Fi, you can run it over many things. It works with the sort of key smart home platforms, Apple, Google, Amazon. So the idea is you don't have to have an Apple house or a Google house or an Amazon house. You can get Matter supporting devices, and they should work with any of these networks. So you have a Matter light bulb or lighting system, and it should work with your Google Home controller or your Alexa or whatever it is. Now, having all that universality, you don't necessarily get for free. So you do need, they do have large, complicated stacks and some communication requirement behind it. So these do push you more towards more powerful devices, more capable devices with lots of RAM, some application space. So you do need these kind of quite powerful devices like our product. So yeah, Matter will probably become, it seems to be the prime, at least for smart home standards. Obviously in things like professional lighting, there are other standards like DALI, but they also have the same issues, that the more you make these things universal and running on layers of protocol, the more you need memory, you need RAM to run these things efficiently. This universality does come with a cost, and all this pushes you towards needing more powerful end devices. So, including Wi-Fi 6 is quite a significant upgrade to the Wi-Fi spec, but it's not one about speed fundamentally. It is about making Wi-Fi more resilient, more flexible, and more efficient, especially in power consumption terms. I think this points it clearly in what one could describe as the IOT space, vague though that term can be. And new protocols can run on it. So things like Matter, DALI, multi-vendor standards are well suited to running on top of this. This does, need, as I say, powerful devices, and I think the product we have is a very easy to use version of a product that will allow you to run these kind of advanced applications. So that's basically it in terms of the presentation. So we have now obviously some time for questions. I didn't think talking at you an hour was really going to be a good idea. So I'd be very happy to receive any questions that you might have on any points raised by the seminar.
Super, thank you, Nick. Yeah, there are some questions. The first one is Wi-Fi now competing with Bluetooth Low Energy?
Well, I think, yeah, I tried to cover this a bit in the, it is to a certain extent. I mean, I think there's a bigger zone of overlap than there used to be, but I think they do still have quite distinctive areas of specialization. Bluetooth is still more resilient, more flexible, simpler to put in place. Wi-Fi still offers higher bandwidth. Yeah, essentially that's probably the biggest advantage of Wi-Fi. It's got much faster. But in that middle zone between the two, yes, there is now some bigger overlap than there was. There's no doubt about it.
What about country certification? Which countries are supported by the module?
So by a standard, we support Europe, including the UK, US, Canada, Japan, and Korea. We do sometimes add other certifications if there's customers particularly interested in them, but those are the ones we support, which covers the main important zones for electronics. But some of our modules have also been certified for China or Taiwan or other countries.
Okay. When will the ISP50-61 be available?
So we hope to have our first engineering samples in the next 4 weeks, towards the end of October, and then fully in production sort of by the end of the year or early 2025. But in terms of having some kits and stuff for people to start developing with, that should be quite soon. Yeah.
Okay. And what is the difference between your solution and competitors?
Well, I would say generally with all our modules, it's basically the same thing. Firstly, we use system and package technology. That means, firstly, we can make them very small. So I don't think there's any solution this size on the market, which has got everything inside in a 12 by 12 millimeter package with antennas. Not that many Wi-Fi modules to date actually have included antennas. Some do, but not so many. Ours does. So you can also connect external antennas if you want. The SIP process is a very high quality manufacturing process, so that does give you a very high degree of repeatability and consistency. And yeah, everything is included. So it just means I'll literally put it on the board, power it up, and it all works. So that's, I would say, the main key advantages of our solution.
Okay, good. So that was all questions I've got from the audience. So I said thank you, Nick, for your presentation. And for the audience, you're welcome to join our other webinars ongoing with Panasonic tomorrow with the next topic about Wi-Fi. And we have in addition a second technology week in beginning of October with cellular and GNSS topics, also with other suppliers then. And hopefully we will see you then again. And yeah. Have a nice day. Bye, Nick, and thank you.
Bye. Bye.